AOPS Volume 1, the basics number 103. Find the smallest positive integer greater than 1, which yields a remainder of 1 when divided by any single digit positive integer greater than 1. So this is basically just a twist up of some previous questions which I've explained on this channel about AOPS questions. So as always, when dealing with remainders and quotients, always use modular arithmetic if necessary. So let's call the smallest integer, well, that's a terrible m. Let's call this integer bm. Therefore, n must give a remainder of 1 when divided by any single digit positive integer greater than 1. So they're single digit and they're greater than 1. So mod 9 is the greatest single digit, all the way down to mod 2, which is the lowest digit greater than 1. So n must be congruent to 1 mod 8, n must be congruent to 1 mod 7, m must be congruent to 1 mod 6, and this goes on until m is congruent to 1 mod 5. Or not mod 5, mod 2. And now with a modular uh, property, which is that if a is congruent to b mod c, then a minus n is congruent to b minus n mod c. And with this understanding, we can subtract 1 on both sides of the congruence to get n minus 1 is congruent to 0 mod 9, m minus 1 is congruent to 0 mod 8. Likewise, m minus 1 is congruent to 0 mod 7. And this goes on until m minus 1 is congruent to 0 mod 2. And what the congruent is equal to some constant standing for is that it means m will give a remainder of 1 when divided by 9, which is the number next to the mod sign. Mod represents modular. So now that with this definition, since each are congruent to 0 mod some integer, it must mean that it's completely divisible by each integer from 9 to 2. Therefore, we must find the smallest positive integer, meaning that we must find the least common multiple between 2 and 9. So if we scroll down to give us some room, because it's about to get messy, we can begin to do so. And to do that, I'm going to do prime factorization. So 9, 8, 7, 6, 5, 4, 3, and 2. 9 can be equal to 3 times 3. 8 is equal to 2 cubed. 7 is 1 times 7. 6 is 2 times 3. 5 is 1 times 5. 4 is 2 squared. 3 is 1 times 3. And 2 is 1 times 2. Now, all I need to worry about is first dealing with the larger integers, because the larger integers contain the factors which are necessary to compose the smaller integers. So 9 must contain two threes. And since we have two threes, that means that we can now cover 3 as well, because the two threes contain one of the threes necessary to compose 3. And I see here that we can move on to 8. 8 requires three twos. So this times 2 times 2 times 2. And now that we have three twos and two threes, we can now compose 8. And now we can also compose 6, because 6 contains 1, 2, and 1, 3, which are present within the current factors. And 4 can also be achieved because we have two twos, and we can achieve 2 because we have at least 1, 2. And now we have the two primes of 5 and 7, so we must multiply by 5 and 7 to obtain the least common multiple. And multiplying this out, we get 3 times 3 to be 9, 2 cubed to be equal to 8, times 35. Actually, I'm going to leave it as is, times 5 times 7. 8 times 5 is 40. 7 times 9 is 63. This is equal to 2,520. So the least common multiple of the integers between 2 to 9 is 2,520. Hence, m minus 1 must be equal to 2,520, since 2,520 is an LCM that can be divisible by m minus 1. Hence, m must be equal to 2,520 plus 1, which is 2,521, meaning that the smallest positive integer greater than 1, which yields a remainder of 1 when divided by any single digit, will be 2,000. Let's see, I actually forgot. So let's scroll down here. Will be 2,521, which is the solution to this question. And this question you will find many times on competition math. So make sure to get fluent with this concept. But nonetheless, the solution is 2,521.